Good morning, everyone. For today's lecture, I uploaded a video. So today's topic, lecture 2. So we're going to discuss on numbers, systems, and codes. So the learning outcome, we focus on at O1, explain digital logic, Boolean algebra, and digital numbering used in digital computer system. Okay. So topics 2. So it's mapped to, as I mentioned, LO1. So why it's important to give knowledge about logic numbering system 0, 1, their calculation and how digital device communicate and transfer information using the logic numbers. So teaching learning strategies, we will develop lectures to lecture notes and tutorials during lecture session. The topic will be discussed thoroughly. So we can refer to this video. And the impact is to you can demonstrate critical thinking and problem solving abilities through solving the tutorial questions, quizzes, and activity in class. Okay, students are expected to pass the examination, test, and final exam. So to this outline, number system. So numbers, decimal, binary, octal, hexadecimal, binary arithmetic and conversion, ones and twos complement and sign numbers. Second, we see is codes. So BCD and gray codes. Okay. So decimal numbers, the column weight of the decimal numbers are powers of 10 that increase from right to left, beginning is with 10 to the power 0 equals to 1. Okay, 10 to the power equals to 1 here. So we have for 10 to the power 5, 10 to the power 4, 10 to the power 3, up to 10 to the power 0. Then we have the decimal part, 10 to the power 91, 10 to the power 92 is not the decimal numbers before that. For fractional decimal numbers, the column weight are negative powers of the 10 that decrease from left to right. So you can see 10 to the power negative 1, 10 to the negative power negative 2, 10 to the power negative 3, and 10 to the power negative 4. Let me change for these guys for some, yeah. Laser pointer. Okay. You see this. So only 10 numbers allowed from 0 to 9. Okay, we only consider 10 numbers. Okay, for this one. Decimal numbers can be expressed as a sum of the product of each digit times the column value of the fourth digit. Thus, number 9240 can be expressed as, if you observe here, 9240, if you can split. So this one will be the what? How you can put this? If you observe here, number 0, 0 times by 10 to the power 0 plus 4 times 10 to the power 1 plus 2 times 10 to the power 2 and plus 9 times by 10 to the power 3. Or we can rewrite as in this form also. Okay, so 9 times 1000, 2 times 100, 4 times 10, 0 times 1. Okay, so now let's say one example. Express the number 480.52 as a sum of values of each digit. So you will get 480.52 equals to, observe, so this one is a 10 to the power 0, 10 to the power 1, 10 to the power 2. So 4 times 10 to the power 2 plus 8 times 10 to the power 1 plus 0 times 10 to the power 0, then plus 5 times power 10 to the power negative 1 and 2 plus 2 times 10 to the power negative 2. So you will get this kind of arrangement. Okay, so this is the form you have to write. Binary numbers. The column weight of binary numbers are powers of 2 that increase from right to left, beginning with 2 to the power 0. Okay, so again, we are beginning with the 2 to the power 0 for binary numbers. So as I mentioned in the previous one, this one also we have a 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, up to 2 to the power 5. So we count from right to left. Okay. For fractional binary numbers, the column weights are negative the powers of 2 that decrease from left to right. So again, 2 to the power negative 1, 2 to the power negative 2, 2 to the power negative 3, 2 to the power negative 4. Okay, only two numbers allowed, 0 and then 1. Okay, only required is a 0 and 1 over here for binary numbers. Okay, so binary numbers here you can see a binary counting equals for numbers from 0 to 15 is shown below. So this is a decimal number. Okay, 0, 1, 2 up to 15, and for this one we have a binary numbers. Notice a pattern of zeros and ones in each column. Okay, so we see here we have a 1, 0, 1, then 0, 1. Okay, and then we have 1, 1 here, and then 0, 0, 1, 1 here, 0, 0, 1, 1 here, 0, 0, and 1, 1 over here. Same thing like this. Okay, this is the pattern. Okay, once you arrange, you get like this. So digital computer frequently have this kind of pattern for the numbers. So they have, you can see 0, 1. So we can have like a numbers in this direction to get a count. How to get this? For example, 0, you don't have any value, you put 0, 0, 0, 0. Number 1. So we have here 0, 0, 0, and 1 here. How we get 1? This one we here is a 2 to the power 0. Okay, so you get 1 here because earlier you already mentioned, right? Only focus number 2. So 2 to the power 0, you get 1. Here 2 to the power 0, you get 0. 2 to the power 1, you get 1. Okay, here. So 2 to the power 0, you get 1. Okay, the same thing. So here 2 to the power 0, 2 to the power 0, you get 1. And then here, if you want to get number 2, you should get 2 to the power 1. You get number 2. And for number 3, you need to have a combination of 2 to the power 1 plus 2 to the power 0. So you get 3. Number 4, to get number 4, decimal number 4, you should go for the third row, 2 to the power 2, and then the rest plus 0 to get this number. And number 5, you see here, 2 to the power 0 plus with, 2 to the power 2 plus with 2 to the power 1. Later we'll see this kind of a pattern. Okay, so this is what we see is between decimal number and binary numbers. This one always refer to the, for digital counters, frequently have this kind of a pattern. Okay, this one to how we can change to decimal number to binary numbers or binary numbers to decimal numbers. So binary conversion, let's look into this. The decimal equivalent of a binary numbers can be determined by adding the column values of all the bits and that are 1 and discarding of all its bits that are 0. So example, let's convert the binary number 100101, okay, 0.01 to decimal. So start by writing the column weight, then add the weight that correspond to each one in the numbers. Okay, so let's arrange this one. So we have over here 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5. I already arranged here. If you expand, so 2 to the power 5 you get 32, 2 to the power 4 you get 16, 2 to the power 3 you get 8, 2 to the power 2 you got 4, 2 to the power 1, 2 to the power 0 is 1, and then same over here 2 to the power negative 1, 2 to the power negative 2. You have these numbers. Now we try to refer to the binary numbers. So now we have 100,101.01. Now we multiply with the numbers over here. Okay, so this one multiply, you get 32. This one 0. Sorry, this one 0. Multiply, you get plus 4. So only got 0, no values, and this one is 1, 0, and then 1 over 4. Combine all this, you get 37 1 over 4 or 37 over 4. So this is how you convert the binary numbers into the decimal numbers. You can convert a decimal whole number to binary by reversing the procedure. So write the decimal weight of each column and place ones in the column that sum to the decimal numbers. Example, convert the decimal number 49 to binary. So the column weight double in each portion to left. Write down the column weights until the last number is larger than the one you want to convert. So convert decimal 49 to binary. So we already rearrange this. Okay, we already mentioned 2 to the power 0 up to 2 to the power 6. And we see here, for 2 to the power 6, you get 64. 2 to the power 0 is 1. But we want number 49. So we take wait until last number is larger than the one you want to convert. Okay, so you see here, this 32 is lower than 49. Okay, then after that is 64. So 49 falls over here. So you take up to 2 to the power 6. So 2 to the power 6. So if you want to add values, this one becomes 0 because if this one become 1, 64 times 1 is already beyond than this 49. We cannot get. So we want to get the number, so this one becomes 0, 64 becomes 0. And then we take this one, 32 times by 1, so we have 1 here, plus 16 times by 1, so, and then the rest 0, and this one is 1. Now let's calculate, see, 32 multiplied by 1, you get 32, plus 16 multiplied by 1, plus, so you already got 48, you left with 1. You cannot take other numbers, you take this one, 1. So 32 plus 16 plus with 1, you get 49. Okay, so that's how you convert from decimal number to binary. Okay, you can convert a decimal fraction to binary by repeatedly multiplying the fractional result of successive multiplication by 2. This is the carry from the binary number. So example, convert decimal fraction 0.188 to binary by repeatedly multiplying the fractional result by 2. Solution. So you see here 0.188 multiplied by 2, you got 0.376. So it's less than 1, so we must just carry 0. 0.376 multiplied by 2, still carry less than 1, we refer to 0 here, so we put 0. 0.52 multiplied by 2, we get 1.501, so we carry more than 1, so mentions 1. Same thing over here, 0.504 multiplied by 2, you get 1.008, so it carries 1. Okay, so you keep on goes, and this one we say 0.008 multiplied by 2, you get 0.016, carry 0. So now the answer for decimal we can say as a 00110 for 5 significant digits. So the MSB is a most significant digit, most significant bits. Okay, most significant bits. So this is what we will take for at least for 5 significant digits. So again, this is we call as a most significant bits. Binary conversion. You can convert decimal to any other base by repeatedly dividing by the base. So for binary, repeatedly divide by 2. Example, again, convert decimal number 49 to binary by repeatedly dividing by 2. So you can do this by reverse division, and the answer will be read from left to right. So put the questions to left and then reminders on top. So here if you see 49 and 2, so you divide. Okay, if you divide, you have, so this is a decimal number and base here. Okay, 49 divided by 2, you will get 24, but you have to carry or remainder is 1 here. So the question is 24, but 24 times by 2, you have 48. 49 minus 48, you carry 1, so 1 remainder on top. Okay, and then this particular 24 divided by 2, so you got 12. So 12 times by 2, you got 24. 24 minus 24, you got 0 here. Okay, now go for this one. The next one is 12. So 12 divided by 2, you get 6. Again, 12 minus 12, you get 0. So this one, 6. 2 divided by 6, you get 3. So you can write say 3. But again, 3 times by 2 is equal to 6. So 6 minus with the multiplication of 2 with 3, you get 6, so 0. For this one, 3 times by 1, 3 times by 2, sorry. 2 times by 1, so 3 divided by 2, okay, 3 divided by 2, and it's minus 1, because 3 minus 2, you get 1 here, remainder 1. And for this one, you times by 1, you got 1 here, and then continue as a 0 until last question is 0. Okay, so this is how you do the arrangement. So the answer is 110001. So you stop and you continue until the last question is equal to 0. The rules for binary additions are 0 plus 0 is 0, sum 0 and carry 0. 0 plus 1 is 1, sum 1, carry 0. 1 plus 0, you get sum 1, carry 0. 1 plus 1, you have 1. 1 plus 1, you got 1, 0. But here, so in this case, we call it as sum 0 and it carries 1. Okay. When an input carry 1, due to previous result, the rules are 1 plus 0 plus 0, we call it as 0, 1. So sum equals to 1, carry 0. 1 plus 0 plus 1, we have 1, 0. Sum is 0, and it carries 1. 1 plus 1 plus 0, you get 1, 0. Again, sum equals 0, carries 1. Okay, 0 and carries 1. 1 plus 1 plus 1, we have 1 and 1. Okay, not 11 because 1 and 1. So you carry sum 1 and carry 1. So let's see example. Add the binary numbers of 0, 0, 1, 1, 1 and 1, 0, 1, 0, 1 and show the equivalent decimal addition. So let's see now. So 0, 0, 1, 1, 1, you get 7. 1, 0, 1, 0, 1, you get 21. So we have to add now. 1 plus 1, as I mentioned, we get 1 and 1. So 1, 0. Okay. 1 plus 1, we get 1, 0. So 0 here, 1 carries up. So 1 plus 1, we get 0 and 1 goes up. And 1 plus 1 plus 1, you have 1, 1. So 1 goes up, 1 goes up. So 1 plus 0, you have 1. And then here is 0. 0 plus 1, you have 1. So you get the answer as 28. Okay. Now the rules for binary subtraction are 0 minus 0, 0. 1 minus 1 is 0. 1 minus 0 is equals to 1. 10 minus 1 equals to 1. With a borrow of 1. Okay. The borrow is 1. So because 0 minus 1 cannot. So 1, you borrow from this side and then you solve it. So you get 1 here. Subtract the binary number 0, 0, 1, 1, 1 from 1, 0, 1, 0, 1 and show the equivalent decimal subtraction. Solution, okay, we can see that 1, 0, 1, 0, 1 equals 21. 0, 0, 1, 1, 1 equals 7. Okay, so you try to subtract. So 1 minus 1, 0. 0 minus 1 cannot. So you borrow from 1 here. You get 1 and 1. So 1 minus 1. Okay. 0 and then you bought 1 minus 1, you get 1 here. And same thing, you already minus the borrow here, so you have to borrow again from here. So become 1 and then we have 1 and 1 here. So you get 1 and this 1 minus 0, you get 1 and 0. And you get 14 over here, equivalent. Okay, so you must remember the borrowing concept. Okay, so you must understand that this one doesn't borrow, but this one you cannot minus, you need to borrow from here. When borrow from here, it appears as 1 and 1. So 1 minus 1 and then 1 minus 1 becomes 0 and then you have 1 here comes down. This one becomes 0 already, so we need to borrow from here. Cannot, we have to borrow from here. And borrow here become 1 and here become 1 and 1. Okay, so from here you might find minus 1, 0, but if an additional 1, it comes down here. This 1 minus 0 become 1 and here it becomes 0, right? It becomes 0. Okay. The ones complement of binary number is just the universe of the digits. To form ones complement, change all zeros to ones and all ones to zeros. For example, the ones in complement of 1, 1, 0, 0, 1, 0, 1, 0 is complement. Okay, because 0, 0, 1, 1, 0, 1, 0, 1. So is whenever 1 becomes 0, whenever 0 becomes 1. In this circuit, this one a complement formed by using inverters. Remember last class I have taught, so becomes using a concept of inverters. Okay, I hope you still remember inverters here. So 2's complement. The 2's complement of the binary number is found by adding 1 to less significant bits of the 1's complement. So recall that ones complement of 1 1 0 0 1 0 1 0 is, this is the ones complement. Okay, already discussed previous slide. To form this two's complement, add 1 here. So you add 1 there. Okay, and then you get two's complement. So you add 1 here, 1 1 0 1 on top. So 1 0, we got 1 here, and the rest same. And this one, if you write in a circuit form, they add on here. Okay, they add 1 here, so the carrying. So you have the bits over here, which is the conversion. So we complement ones first, and then to do second to two's complement, you have to add 1. Okay. Signed binary numbers. So there are several ways to represent significant binary numbers. In all cases, the most significant bits in a signed numbers is the signed bit that tells you if the number is positive or negative. So computer use more modified two's complement for signed numbers. Positive numbers are stored in a true form with a 0 for the signed bit, and negative numbers are stored in a complement form with a 1 for signed bit. Okay, for example, the positive numbers 58 is written using 8 bits as 0 0 1 1 1 0 1 0. Okay, so if you count here, we have it's 8 bits, bit 1 2 3 4 5 6 7 8. So we write in true form. So we have a signed bit 0, and this one calls the rest calls a magnitude bits. So this positive number is written using the 8 bits. Okay, to get the number of present of this decimal number of 58. Negative numbers are written as a two's complement of the corresponding positive numbers. So the negative numbers, negative 58, is written as, so negative 58 here. So we have here negative 58. So we can write as complement, two's complement. I still remember, right? So two's complement. So we can find a two's complement, and then you can see the sign bit here. Okay, and then this is a magnitude bit. So again, negative numbers are written in the two's complement of the corresponding positive numbers. Two's complement. Still remember how we do that? An easy way to read a signed number that uses this notation is to assign the sign bit a column weight of negative 1 to 8 for an 8-bit number. Then add the column weight for the ones. So example, assuming the sign bit is negative 1 to 8, show that 1 1 0 0 0 1 1 0 is equals to negative 58 as a complement of a sign number. So column weight. So if you see here, column weight negative 1 to 8, and then we have the rest is a 64, 32, 16, 8, 4, 2, and 1. So if you write this, you can get this is 0, 1, 1, 0, 0, 0, 1, and 1. If you multiply it, okay, if you multiply this one, we want to get the negative 1 to 8. So negative 1 to 8 multiplied by 1. So negative 1 to 8 plus 64 times by 1, you get 64. There are 0. 4 times by 1 equals to 4. 2 times by 1 equals 2. If you add on, you receive negative 58. Okay, as I mentioned, this is a sign bit, the rest the magnitude bit. This one, if you want to get the negative numbers to be written as the second complement of the corresponding positive numbers. Using the sign number notation with negative numbers in two's complement from simplified addition and subtraction of signed numbers. Rules for addition: add two signed numbers, discard any final carries. The result is in the signed form. Example here. So if you see 0 0 0 1 1 1 1 0 plus 0 0 0 0 1 1 1 1. So if you plus that using the addition, you get the final value, which is equals to 45. Same thing. If you observe, this is the positive number and this is negative, right? It's 17. We have a sign bit over here, is 1 here. So if you add on, you get these answers, which is negative 3. Okay, you can check also one. Same thing goes here. Negative 9. But here, the addition 1 here, we discard the carry. As I mentioned, we discard the carry. So just take these numbers only, these bits only. arithmetic operation with the sign numbers. Note that if the number of bits required for the answer is exceeded, overflow will occur. Now this occur only if both numbers have the same sign. So the overflow will be indicated by an incorrect sign bit. So two examples. Okay. So 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 1. So POS 64, POS 65. If we add on, we assume we get negative 27, which is wrong. The answer is incorrect and the sign bit has changed. Okay. We know that if positive numbers, the sign bit is not 1 here, it's supposed to be 0, but the answer is negative, so different. This is wrong. Now here, in this case, we can see that this is additional 1 over here. It's a discard the carry. We have 0, 0, 0, 1, 0. So positive. So this is the answer is incorrect and the sign bit has changed. So we need to always note that if a bits required for answers is exceeded, overflow will occur. Okay, so we have to be careful on this point. So the overflow, always remember, will be indicated by an incorrect sign bit. Okay, we have to check always if you got any overflow number. So this one only occur if both numbers have the same sign. Okay. So subtraction for arithmetic operation with sign numbers. Rules for subtraction: 2's complement the subtrahend and add the numbers. Discard any final carries. The result is in a sign form. So repeat the example done previously, but this one is a subtract. Okay, same concept using subtraction. Okay, you have to subtract, then you get the values for 2 complement, subtract and add. Following same concept, you have to borrow, and then you can observe the answer, and then you have additional 1 here, discard the carry. So 15. Same goes here, same concept. If you do subtraction, you get answer 31. And for this one, you do subtraction, you get the plus 7. Again, here we have the additional 1. This is the carry. Okay, anything beyond this, we have additional over here, we discard this, the carry. Okay. Now hexadecimal numbers. Hexadecimal uses 16 characters to represent numbers. The numbers 0 through 9 and the alphabetic characters A through F. So large binary number can easily be converted to hexadecimal by grouping bits 4 at a time and writing the equivalent hexadecimal character numbers. So 0 to 9, hexadecimal 0 to 9, binary, this is the way we can write it, until 101, and 10 until 15 we represent in the numbers. Okay, we represent in the numbers. So start with 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1 under hexadecimal. So example, if you want to express 1001, 0110, 0000, 1110, decimal 2, okay, in the hexadecimal. Okay, from binary to hexadecimal. Group the number by 4 bits starting from the right. Thus, we get the 960E. Okay, 960E. So we can observe that 1110 is E. So this one is E. 0000. This one represents as the hexadecimal 0. 0110. Sorry guys, let me activate this one. Okay, my apologies. 0110. 0110. You get 6 over here. And then 1001. 1001, you have 9 here. So we can write as a 960E. Hexadecimal is a weight number system. the column weights are power of 16, which increase from right to left. Okay. So column weight 16 to power 0 is 1, 16 to power 1, 16, 16 to power 2, 256, 16 to power 3 is 4096. So example, express 1a to f 16 in decimal. So solution, start by writing the column weights. Okay. So now we can check and write now. So we can have 4096, 256, 256, 16 and 1. Okay. From here. And then I represent which is with this one. So I mentioned 1, A, 2, and F for decimal 16. Yeah. We're looking into hexadecimal. Okay. So F we can look into this one. So we here is 4096 multiplied by 1 plus A. A is 10. 10 multiplied by 256. And then 2 is 2 here. 2 multiplied by 16. And F represents what? As 15. Okay, F represents as 15 multiplied by 1. And you get 6703 to decimal. Okay, this is how you convert to decimal. Octal numbers. Octal uses 8 characters, numbers 0 to 7 to represent numbers. There is no 8 or 9 in a character in octal. Binary number can easily be converted to octal by grouping the bits 3 at a time and writing the equivalent octal number character for each group. So example, you have 1, 001, 011, 000, 001 and 110. Okay. So in octal, if you are writing in octal, so from binary you are writing in octal. So group the binary numbers by 3 bits starting from the right. So from here, if you can write this, we can check that 110. You can check on the 110 how we can observe the numbers. Okay, so group the numbers by 3 bits and starting from the right. Thus you can get 113016. Okay, for octal characters. Octal also weighted number system. The column weights are power of 8, which increase from right to left. So 8 to power 0, 1, 8 to power 1 is 1, 8, sorry, 8 to power 2 is 64, 8 to power 3 is 512. So example, express 3702 octal in decimal. So octal to decimal. So we write 512, 64, 8 and 1, and then we try to multiply by the 3, 7, 0 and 2. So 1 to multiply and add on, you get 161986 in a decimal number. Okay. Now BCD code. Binary coded decimal BCD is a weighted code that is commonly used in integer system when it is necessary to show decimal numbers, such as in clock displays. Okay, this one. So this clock displays. The table illustrates the difference between straight binary and BCD. BCD represents each decimal digit with a 4-bit code. So notice that codes 1010 through 111 are not used in the BCD. Okay, we can check that. So notice that code 10110 through 111, 1010 through 111 are not used in the BCD. This is important, man. Understand this. You can think of BCD in terms of column weight in group of 4 bits. For an 8-bit BCD number, the column weights are 80, 40, 20, 10, 8, 4, 2, 1. So we can read 1, 2, 8, 1, 2, 4, 8, 10, 20, 14, 18. So for example, what are the column weight for the BCD number 1000, 0011, 0101, 1001? Now let's see how we can do this. So now let me expand. We look into the green one. Okay, the first one, 1001. So we can write as 1, 2, 4, and 8. 0101, we call it a 10, 20, 40, and 80. This one 100, 200, 400, 800, 1000, 2000, 4000, 8000. Now try to compare this bit and these numbers, decimal numbers. Okay, let's compare. So from here, note that you can add the column weight where there is a 1 to obtain decimal number. For this case, 1 is observed, so observe from here, 1001. So 1001. So I take 1 and take 8. This both become zeros. And this one, 0, 1, 0, 1. So we have 10 and 40. So 10 and 40. 0, 0, 0, 1, and 1. So 1 times by 100, 100. 1 times by 200, 200. 1, 0, 0, 0. 1, 0, 0, 0. So these three numbers become 0. You only have 8000. So 8000 plus 200 plus 100 plus 40 plus 10 plus 8 plus 1. You can decimal is 8359. Okay. So this is how you have to split up for the 8-bit BCD grouping numbers. The next one, gray code. Gray code is an unweighted code that has a single bit change between one code word and the next in a sequence. Gray code is used to avoid problems in the system where an error can occur if more than one bit changes at a time. Okay, so gray code is used mainly to avoid problem in the system where an error can occur if more than one bit changes at a time. So now let's see this one. Convert the binary number 11000110 to gray code. So solution, the first one, A, you get like this. So normally how we can do that, we see for the grouping. We see for the grouping. First one, you come down. Okay, you can write as 1 here. And then you check 1 and 1. These two. Okay, you check this 1 and 1. If same, we write as 0. If not same, we write as 1. Okay, 1, you first put down. So 1, 1, you compare. So 0. 1, 0, you compare, which is 1. See here, you must understand that if you comparing two bits, if the same, we can write as 0. If not same, we write as 1. So 1, we come down. 1 and 1 is same, right? We put 0. And then 1 and 0, not same, right? We put as 1. 0 and 0, same, you put 0. 0, 0, same, you put 0. 0 and 1, okay, you compare, you put 1. 1 and 1, same, you put 0. 1 and 0, not same, you put as 1. This is how you convert binary to gray code. Now, how you convert gray code to binary? So now we see, if we want to compare gray code and binary, so we have this one, your gray code, you want to compare to binary. So 1, you put down, okay, and then you compare 1 and 0. Okay, not same, right? Put as 1. And then 0 and 1. Okay, we got same, right? Sorry, you compare in this way. Sorry, this is 1, you come down. Okay, and then you compare 1 and 0. You see 1 and 0. Say they are not same, you put 1. And then you compare this one and this one. They are same, right? You put a 0. So this 0 and 0 compare. The same, right? We will put 0. But this 0 and 1 not same, you put as 1. 1 and 1 same, you put 0. 0 and 1, they are not same, you put as 1. 1 and 1, they are same, you put 0. This is how you change to gray code to binary code. Guys, I'll repeat again this part. Please carefully listen. Now you have to compare. Let me see how we can draw this one. So, okay, now let's see again. So 1, okay, this is binary to gray code. So binary to gray code. So you have binary 1, 1, 0, 0, 0, 1, 1, 0. So first you see this 1, you put down here, and then you compare. this one. Okay, so I put here if same equal as 0, no, not sorry guys, I don't have my notepad with me. I have to use mouse here. Not same, you put as 1. Okay, now if you compare, first you have 1, you put down, and then you compare 1 and 1 same, right? You put a 0, and then you compare these two, 1 and 0 not same, put 1, and then this one 0 0 same, you put 0, this one 0 0, you put 0, 0 and 1 not same, you put 1, this one 1 and 1 same, you put 0, this one 1 and 0 not same, you put 1. Okay, now you get the gray code. Now number 2, convert gray code to a binary code. So I take the gray code here, 1 0 1 0 1 1 1 1 1. Okay, so now gray code 1 0 1 0 1 1 1 1 to binary. So 1 you put down, and then this 1 you compare with 0, you compare this. 1 0 is same, not same, you put as 1, and then you compare 1 and 1 same, you put 0, and then this 0 compare with this 0 same, you put 0 here, and then you compare 0 and 1 not same, you put 1, and then here 1 and 1 same, you put 0, this one 0 and 1 not same, you put as 1, and then 1 and 1 same, you put 0. So now you have 1 1 0 0 1 0 1 0, which is in the binary. Okay, so this is the concept. So overall summary, so from decimal guys we study, so you must remember decimal. This is what we see. From decimal you can go to binary. Okay, division 2 or COW, not cow, yeah, is a column of weight. Okay, what's the weight carries. So division 2, and then COW, column of weight from binary to decimal. We see this one first now, and then we also observe for hexadecimal. Okay, division of 6, division of 16, and then column of weight. Observe this. Binary division of 2, hexadecimal division of 6, BCD group of 4 bits. Okay, octal division of 8, and then column, we are from octal to binary, column of the weight, we have to multiply. Hexadecimal to binary, we have to group of 4 bits, and then from binary to octal, group of 3 bits, and then last one we observe using the conversion technique. Okay, by comparing same or not same, do the conversion. Okay, this is the overall summary that we discussed today's class. Okay, so try to remember for this module, for this topic, you must know about the table, how the conversion happened for the hexadecimal division 16, binary division 2, decimal division of 8. So you must remember this, and then you must know for the gray code and also for the BCD how conversion happened. This is important. We have to practice this more so that you can familiar with this. Now application. So in the previous slide previously in the my time, this slide I put first, but I put it at last now, so that you can easily understand, because we have studied the binary codes and so on, right? So normally this one you can apply in a MCA 68K assembly language, okay, for the microchip chip. So we can apply, like, you want to do a programming, you want to add your coding, so you can use in the particular microchip chip. So you can define the port A, port B, port C, port D, and port E. So you can see the input is 1, output 0, how you can compare that. So you're going to use in a microchip application, and you can also in the 7-segment display and so on. So you can apply in this kind of a use case applications. So it's important for you to understand this, okay? So you might have a project that we must use, let's say, for example, like a microchip. On that microchip, you must understand the ports and how you're going to use the binary codes and so on. Okay, this is important. This is for your applications. You might see this more when it comes to your project. Okay, you have a project, a group project for not for this particular module, but the future year 2, year 3 is a group project with Dr. Nurul. Then you will see how you're gonna apply this. Okay, important. Thank you for your attention all. So that's all for today's class. Okay, thank you.